Take some time. All right. Welcome, everyone, to Electronic Devices and Systems. So, can I have a show of hands who did not attend 275? Yeah. New to this electronics unit? You did attend. I saw you. Okay. All right. Yeah, so we have many people who attended 275. And so this is a continuation of what we learned in 275, which is non-linear circuits, devices and circuits. So if you haven't done 275, you can always go through a electronics textbook that we will mention here, and make use of the consultation hours, come to us, ask questions, and catch up with what is the requirement. So we will go through the introduction to the unit and the prerequisites for this unit. And this unit will be co-convened by me and David here. Most of you know both of us. So about this unit, why we bother to study about electronic devices and systems, because it's everywhere, from our cell phones to big communication towers, and cars, and you name it, it's there. And analog electronics is important because that is the real world is analog. It's not digital. So every interface, the interface from the world to a semiconductor system, and also the output side, the semiconductor system to the real world, it's all analog, right? Like, so input side would be, an example would be a microphone, and the output side would be, say, a power amplifier. So, so this is us, myself, Binesh, and David here will be taking some topics, in half of the topics in this unit. And your tutor will be Mohammad Kasif, who was your lab demonstrator last semester. And yes, there's a reminder for you to read the unit guide. How many have you read the unit guide so far? Okay, that's more than I expected. But please read the unit guide. So if you have any confusion about how it's going to work out, just let us know. Okay, but it is important. At least read the bullet points or the section headings and find out how it'll be assessed, what are the tests in this. We also cover some of it in this lecture. So, you want to go on?
So, just to introduce myself to those of you that don't know me, I'm the co-convener for this course, Dr. David Payne. Same for Binesh. We recognize a lot of you from ELEC376, 675, but some of you will be new. So for the new people, the way we structure this unit is that we'll cover different topics each. For 275, it was kind of half and half. This one's a bit more mixed in, so I'll be here in 3 weeks to teach you differential amplifiers. And then Binesh will take over again, and then I'll come back in to cover power amplifiers. So I encourage you all to look at the weekly schedule, which is there. That tells you all the topics every week, the chapters in the book that you can read to kind of work out what's happening in those areas and who's teaching it as well, so you'll know what's happening. And just before I leave as well, just for those that did 275, 675, just want to say thank you for those that filled out all the feedback forms. So we're going to take that on board. We've got lots of comments, lots of positive, a couple of negative, and we'll try to bring some of that into this, so you'll directly benefit, hopefully, from those forms. And of course, we'll be making you fill them all out at the end of this unit. And I know it's a hassle, but we do appreciate that. So I'll leave you now with Binesh, and I'll see you. I'll be in and out of all the labs, but yeah, I'll definitely see you all in the next lectures. I'm doing differential amplifiers. Okay?
Thanks, David. So the goals of these units are here. you can read it. So we will be covering some sections that we learned in 275, which is diodes, BJTs, MOSFETs, the basic of it. And we'll also go into some of the electronic systems, mixers and power amplifiers. And what we will looking is how it works and what are the high frequency responses to that system and how do we design circuits. We will build circuits and debug, simulate them in the labs. And in the end, we will equip ourselves with a few tools that we can use maybe when you take up a career as an electronics engineer. You can use those tools. So these are the main textbooks. Microelectronic circuits by Cedra and Smith would be something that I'll be closely following. And I guess David also will be doing the same. Also will be occasionally referring to Hambley. So also for mixers and nonlinearities in this semester, we have a new textbook. It's a RF Microelectronics by Razavi. But this textbook is quite involved and much more higher level than required. So I'll be preparing detailed lecture notes for these sections that requires RF microelectronics. So don't worry when you go through the first few chapters of this textbook. I would have scared at your age, but I'll try to make it up for you by providing a better lecture notes or maybe additional reading materials for that. So the learning outcomes, quite similar to 275, but one difference here is this unit is heavily emphasized on active self-learning. Okay, so it's not, except for the first week, it's not just the lectures. So we don't have lectures. We will have lectorials, so lecture plus tutorials. Okay, so and we don't have tutorial sessions per se. So all the lectures will be in online videos and reading materials that you can watch and go through some online quizzes. Then you come to the classroom where we will solve quite a number of problems and go in depth in each topic. Okay? Does that sound good or bad or not sure? Okay, yeah, so that'll give you enough time so you don't have to learn in that 1 or 2 hours. You have 1 week to learn stuff at your own time, wherever you want. And then the quizzes close just before the class. So we can go through who made the most mistake, not who made, like which question was difficult, and we can focus on those topics. So we'll deeply understand the basic semiconductor devices and transistor amplifiers, which includes both BJTs and MOSFETs. We will look into the frequency domain responses of these amplifiers. We will design some power amplifiers and implement them in the lab. So this is the weekly plan that David was talking about. So just like in 275, we have made a weekly schedule for each. This is available on iLearn for you to download. What I have done is I printed it out and pasted it next to my seat in my office. So you can do that the same if your landlord agrees. Just use blue tack. So this is where we are. Even though it says online learning content, the first week is an exception because we need to give you an introduction of how the unit is structured. So we will have a online learning there. So it'll be videos or lecture reading materials. Then online quiz starting from week 2. So this quiz won't be very difficult. This is to just make sure that you go through the learning content. Okay, so if you watch the videos or read the reading materials, it will be very easy to score 100% on the online quiz. Okay, and also to make sure that who is doing it and who is just skipping everything, so that I don't need to catch you the last minute, so I can find out if you have any trouble with early on. Then we will come to classroom here, where we will review the topics and go in depth on some of the following topics, and do problem solving, and you can ask questions here. Okay, that's the consultation. So as David said, I will cover the first 3 weeks, where we will learn BJT and MOSFET amplifiers, which overlaps with the last unit that you took. And then David will come back for differential amplifiers. And then again, I will take the nonlinearity and mixes. David will take the remaining power amplifiers, and we have given 1 week here for system integration. So we talked about individual systems, say it's power amplifiers, say it's BJT amplifiers, like a mid-band amplifiers. But what happens when we integrate those systems? So how can we integrate it? What are the design requirements? What we need to consider when we integrate it in a big system? For example, giving the output of one system to the next. So what happens? Like what can go wrong and how we prevent it? Yeah, the references are there. So we have 4 take-home assignments. Those will be like I-Learn quizzes, like last unit. And in laboratory sessions, the same structure as in 275. We have 4 laboratory work modules, but there are no tutorials. So tutorials will come to the classroom. But we have provided 2 extra workshop sessions so that you can practice for your exam, final exam. And 2 of those requires lab reports. So you get 3 weeks when the unit is on, you get 3 weeks per lab report. So I made this slide to give you a shortcut path to being an HD student in this unit. So if you follow this path, you can score an HD after the final exam. So one is self-learning from the materials provided. Then attempt the quiz, where you will test your knowledge yourself. You will find out what you know and what you don't. And you can bring your doubts to this classroom here, where you clarify your questions and solve problems and learn from examples. And in the lab, do the pre-lab activities before you go into the lab, and then actively participate in the lab, and then write lab reports. Okay, and then do assignments and attend exams. So don't need to be told for that. So one thing to make sure is you make use of the consultation time, which many of you did not make use of. So I have 2 hours per week just for consultation. So answer any of your questions, technical or otherwise. Right? So you can check I-Learn to when is the consultation hours and what time it is, and for both me and David. So you make use of the consultation hours, and don't wait for the last minute. You can come even the first week itself. So feedback. So many of you won't answer questions loud, but we have set up an active real-time feedback system that's called the Poll Everywhere. This is how you, if you are new to this unit or new to the, if you haven't attended 275, you can use your mobile phone and type in your browser that, and you will see the poll. Can everyone do that now, please? So you can either do that every time, or you can install a Poll Everywhere app, which will give you a really good shortcut. So you just need to open the app. If you have set up, can you say yes, and we'll see if it works or not.
What are the last three numbers?
Sorry?
Just
Oops. Three, 5, 4. Sorry, I didn't catch you properly. 5 people say yes. 7. You can also say no. Still, I will know. Yeah. So we will use this tool when we solve problems, or when I require your feedback on whether the topic was tough or not, whether to look at it again or not. So, well, we are using a free version of this, although the school has promised to buy it for us. So I think the cap is 25 or 30. Maybe it's 50. 28. Okay, probably it's 50. But that's good. Okay, you can do that later, but thank you. So the thing you were waiting for, the assessment. So here the final exam carries 40 marks out of 100, so 40%. And we have a mini exam before the final exam. A mini exam will be in week 12. You can see in the schedule we have a mini exam here in the classroom. So that exam is designed to help you prepare for the final exam. So it will be in the same format, but it will be only one hour. Okay, the same format, but the number of questions will be different. So I'll give you an idea of where you stand and what you should be focusing on. And online quiz, each week's quiz carries half a mark. So we have 10 quizzes, so total is 5 marks out of 100. And 4 assignments will carry 20 marks in total, and lab will carry 30 marks. So in the case of laboratory, we will be simulating, constructing and measuring circuits, just like in the last semester. And 2 of those lab sessions in week 12 and 13 will be used for workshops. So arrive on time, revise lecture notes, complete preliminary work, which carries 20% a mark. And you need to have a logbook, which you have to keep throughout the semester. And we will check the logbook and give you marks for that as well. There are 2 lab reports. So there was one feedback that you didn't understand how the marks were given for the labs, right? So here is the mark distribution for the labs. So 20 marks for the pre-lab out of 100, and 20% for the logbook, and 60% for the participation and results. And in that 60%, 40 goes to results and explanations, 10% for bonus questions, answering bonus questions, and 10% for active participation. Okay. Any questions on that? Raise hand. Okay, so we are facing a problem. So last year there were around 40 students. This year we have 85. So we had 2 labs last year, and we had to open 2 more. And labs are absolutely dependent on so many things, like what is the lab available, and the students' classes clashing with other classes. So I got several emails saying that they have clash with other units. But when I look at the lab, you can see it's all full, 100% for all the labs except for 376 on Tuesday, Tuesday 9 to 12. So is there anyone here who is enrolled in the Friday lab, want to switch to Thursday lab? Yeah. So is there anyone here who is in the Thursday lab, want to switch to Friday lab? Friday we have from 1 p.m. to 4 p.m. Friday afternoon. That's what I expected. Nobody wanted to switch to Friday lab. So people who have clash with the other units, yeah, so there's not much I can do. So one thing you can do is find, if through your friends, find if someone wants to swap with you. And if that is the case, then let me know and I will update in the register. Okay? You need to have friends first. So, yeah, so that's a problem. Okay? So we have a Tuesday lab which is quite free. So if you have clashed on Friday, you can register for Tuesday. Okay, so I've received a few emails and I noted down the people's names, but I can't do anything. I can't force anyone to change their labs. So it's out of my control. Yeah? Let's go to assignments and tests. So you can read this on your free time. The assignments will be in iLearn. The solution will be posted after, or within 2 weeks after the close of the assignment. And the mini exam carries 5%. Will be conducted in this classroom on the week 12. It will be an invigilator test. And online quiz will be weekly, and it will be posted on the next day after the lecture. That means your week 2 online quiz will be, and online learning content will be posted tomorrow. Okay? Have anyone gone through the iLearn page for this unit? Yeah, so is it clear about the different sections that you need to go through? So if you have any late notices or absences, just go through the official path to student services and raise a formal notice of disruption of studies. Okay? So let me check if I can open the iLearn page. Just so this is where the online contents and the quiz will be, and what we will discuss in the classroom slides will be here in lectorials, and then your next week's lab work module you can find here, lab work module 1 for week 2, 3, and 4, and the assignments will appear here. Okay. So very simple structure. Any questions? Yes?
So the fees will start next week, not this week?
Not this week. So it will open tomorrow, and it will be open until next week, until the lecture starts. Okay, the lecture starts at 1 p.m. So the quiz will be open till 1 p.m. Okay, so you have one whole week to attempt the quiz, and the quiz will be very simple. If you have watched the videos and learned the content, it will take you less than 10 minutes. Okay? Yes? You have any question? Okay. Yes?
Can we start this lecture 10 minutes afterwards? If we have to come all the way from Water Road, we just finish the morning, we have a project practice there.
9 to 1.
Okay. How many people have that issue? Okay, quite a lot. So yeah, okay. So
Maybe spend the first 10 minutes reviewing the quiz.
okay.
That's not missing.
Yeah. Okay. Yeah, so I can do something which does not affect what comes after that 10 minutes, and then you can, if you want, you can catch it up on Echo 360, and still you won't miss anything later. Yeah, that's possible. Thank you for the feedback. Anything else? Anybody want anything more? Can you see there? Can you see that? All right. So we'll go to the technical part of this unit now. It's a bit slightly more difficult than 275, I would say. And I'll keep constantly referring to 275. If you have any questions, let me know. Okay, right then on and there, or later after the class, or during the consultation hours. Okay. So the first here we'll be reviewing diodes, BJTs, and MOSFETs. It's like everything that you learned last semester, reviewing in 1 hour. Okay. So a diode, it's a two-terminal semiconductor device. Okay, it's the simplest device. Is there a one-terminal device? Anybody? If there is no one-terminal device, why wouldn't be? What would be the reason for not having a one-terminal device? How about an antenna? Is it a one-terminal or two-terminal? It is still a two-terminal device, so it's a dipole antenna. It's still two-terminal. So diode is the simplest component. It's a two-terminal device, and it's the mechanical equivalent of it is a valve. So valve which let a fluid flow through one direction, but closes or does not let the fluid flow the other direction. It's a mechanical equivalent for a diode. So in terms of in electricity, the diode let current flow in one direction. So this is the symbol of a diode. It lets current flow in this direction, but does not let the current flow in the opposite direction. Okay, so that will give rise to a IV curve like this. So when the voltage is positive, you have a large amount of current for a small voltage. And when the voltage is negative, you have zero current for whatever voltage you apply. Okay, that's the ideal diode. And the insides of a diode, it's a p-n junction semiconductor. So p-n junction, what makes it a n-type, what makes it a p-type, has to do more with solid-state physics, which is out of the scope of this unit, but I believe everybody has a proper background on the semiconductor physics, right? So you know what is doping, what is p-type, what is n-type, and electrons and holes. So all those come into picture when we talk about a semiconductor p-n junction. So how do we make a diode? This is a simplistic view here of a p-n junction diode. You take a p-type material and you place a n-type material on top of it, and you form a p-n junction. Okay, but in reality, there are multiple steps to making a diode. So these diodes are made in big semiconductor foundries where people wear bunny suits and really neon lights and very ultra clean rooms. And they work there for many hours to create diodes for you. And here is the picture of the first transistor. What was that? It was a germanium transistor. It was the one you see here, clear part, that is plastic, and a kind of a resin. And germanium piece is here on the bottom. And so the symbol of the diode came from the first transistor, which looks like that. Right. So now you know. So explaining the p-n junction requires quite an involved p-n junction theory in solid-state physics. So I'll try to explain it in so n-type semiconductor, you have a valence band, a conduction band EC and a valence band EV, and there is a Fermi level which is very close to the conduction band. So that means there are free electrons in the conduction band. Free electrons means that is not bound to the atom. They can flow through this semiconductor. When you apply a voltage, the electrons will go from one point to the other. Similarly, you have this is the p-type semiconductor where you have Fermi levels here and you have holes in the valence band. Okay, holes in the valence band are also not bound to any atom. They are loosely bound to atom, and apply a external voltage, the holes can move through the semiconductor. So you have n-type semiconductor here and a p-type semiconductor here. And now to make a diode, all we need to do is to bring them together. Okay? So what happens when we bring the n-type and p-type semiconductors together is just like water level stays the same, there is a rule that the Fermi level should remain the same if it is a steady state. So Fermi level, which is here, should align. That means your valence band and conduction band will form like this, and there is a sharp barrier. So I told you we have electrons here and holes here. Now the electrons cannot go to the other side and holes cannot come to this side unless you apply an external voltage. So there are two ways to applying external voltages to a diode. One is forward biasing. That means you apply positive voltage to the anode and negative voltage to the cathode. So here is your diode. This is the anode and this is the cathode. You apply a positive voltage to the anode and negative voltage to the cathode, you get a current flow, because now you are applying a positive here and a negative here in terms of junction theory. Okay? So what happens when you apply a positive voltage to a bunch of holes there? You get rippled. So you're kind of pushing the holes this way and pushing the electrons onto the junction. So the electrons and holes, they cross over the barrier and go on the other side. So that's how the current flow through the PN junction there. Okay? And what happens now if you decided to apply a negative bias or a reverse bias there? Now you are applying a negative voltage there and a positive voltage here. Now you are pulling electrons out on one side and pulling holes to the other side. So there will be, initially there will be a current, but after all the electrons and holes are removed, there will be zero current. Okay? There is no more carriers left to flow. So there will be zero current. So that is how the diode works. The diode equation is what governs the current flow through a diode. And you can see it's I naught times an exponential term minus 1. So some applications we ignore that minus 1 because it's quite small compared to the exponential term when the voltage is quite high. Okay? So what can we say about the diode? Is it a linear device? What would you name it? What kind of device is it? It's an exponential device, right? And so that is heavily nonlinear, right? So as you can see from this graph, it's nowhere linear. It goes like that. But for some of the applications, we can consider a tiny part of this curve and consider it as linear. So that's what we call a linear approximation. Okay? So what do we use these diodes? So there are plenty of applications. We start from rectifiers, solar cells, photodetectors, mixers, LEDs, optocouplers, voltage regulators, and lasers. So there are plenty of applications for diodes. One of the interesting applications is photodetectors. In many of these applications, diodes work in the forward bias. In photodetectors, diode work in reverse bias. Okay, so how it works is here we saw if you apply a positive here and a negative here, you pull the electrons and holes away, so there is no current flow. And when light comes and hits the semiconductor, it creates a new hole and electron, and immediately that gets swept away. So each photon coming onto the semiconductor generates a current. A pair of electron and holes, and that gets swept away, that means a current. So a current per photon, which is a photodetector. Okay, you shine light on it, and it produces current. Okay? So photodetectors, you can use it to find out any spectrum, whether it is day or light, so day or night, or whether it's what is the intensity of light, so power meters, spectrum meters, and so many applications like that. So that is the diode equation there, and the I naught, which is the reverse saturation current, is this term. So the reverse saturation current is again heavily dependent on the device geometry, the temperature, what kind of material is used to make the diode, and so many other factors come into picture. So you can see the geometry is included in the terms A and yeah, that's the only term, A. So if it is a big junction, or the area of the junction is large, then you have a large leakage current or a reverse saturation current. So can you find the analogous to this reverse saturation current in a mechanical valve? So what is it? What could be the equivalent of a reverse saturation current in a mechanical valve? We said the diode is equivalent to a mechanical valve, right? So what is reverse saturation current equivalent to? Backflow, yes, that is the answer. So you want the valve to completely close in the opposite direction. So you want it to let the water flow in one direction, but close it completely in the opposite direction. Imagine there was a leakage. So one direction it flows, and the other direction water still keep flowing, but with less quantity, a trickle down. So that is the reverse leakage current or reverse saturation current, right? So the bigger the reverse saturation current, it deviates from the ideal diode behavior too much. So we need to keep the reverse saturation current small as possible. Okay, so for that reason, when you design photodetectors, you go for a very tiny size. So there are 1 micrometer diameter photodetectors because the A is quite small, so the I naught is quite small. So that is to reduce noise. But if you want to, so I have the question here. If you have a photodetector and you want to maximize the signal, not the noise, maximize the signal, which of the 3 photodetectors will you use? A, B, or C? C? Look at the equations. So what are we working? So looking at the equation, each photon incident on a photodetector creates a unit of current, right? So you want to increase the number of photons incident on this semiconductor. That will increase your current. And I said the photodetectors work in reverse bias. So that means the voltage here is a negative V, and that term is close to 0, right? E power minus some large number is close to 0. So that is negative I naught mostly. So the current you get through this photodetector is reverse saturation current. And you want to maximize that current in a photodetector if you want a high signal. Okay, now you see how you need to balance it. So on one side, you want to reduce the noise, so you want the I naught to be small. And on the other hand, you want the signal to be large, and you want I naught to be large. So that is the kind of design considerations that you come across when you design components like this, or choose components to design systems. Okay? So the answer here is A. So you want it to be as large as possible.
Guys.
Too late. You guys are fast. By the way, this is not assessed, and I have no way to know who answered what. So feel free.
You were still 50-50 when you were done
Yeah.
explaining, so.
So let's look at what happens when we have an issue with temperature. We have an electronic circuit working in room temperature. So that was the assumption for basic electronics. So we don't consider a change in temperature. But the in the reality is the temperature has a big impact on electronic devices. So you will see your computers have cooling fans for a good reason, and some supercomputers, they need liquid nitrogen cooling systems. So that's for another good reason. So even a diode behaves differently under different temperature. So let's say at room temperature, 25 degrees, that's our IV curve. So now the diode is on. Let's assume a lot of current is flowing through this diode. So that means that the diode is heating up. So the temperature is increasing. So when the temperature increases, the voltage required to turn the diode goes down. So if this was 0.6, at higher temperature, now it is much lower, less than 0.5. So that means if you apply a constant voltage, more amount of current is flowing through this diode. And then in effect, it's heating up the diode more. So that forms a vicious cycle here. Higher current means higher power dissipation. Higher power dissipation means higher temperature. That leads to higher current. And then it keeps going until the device completely gets damaged. Okay? So that is called a thermal runaway here. So that is an unstable situation that often electronic design engineers face, the thermal runaway. So temperature is one of the key parameters that you have to consider when you design a system. But although in our labs, we don't consider temperature, we always assume it is room temperature because we don't work with large amount of currents. We use small signals. But if you are designing a power amplifier, you have to also consider temperature. So you remember working with, no, you did not work with power transistors last year. So when you work with power transistor, they are big and they have cooling fins, so to keep it cooled down. So it is designed that way. So I talked to you about the linear approximation, of the IV curve, which is quite non-linear, we can take a small section of that and consider it as linear. Okay, so let me so in this IV curve, so if I have a voltage of VD flowing through this diode, and the corresponding current of ID is flowing through here, what is the slope of this curve? The slope is y divided by x, or delta y divided by delta x, right? So delta y is delta I, and delta x is delta v. Okay, now it's not VD, it is delta VD. It's VD is say 5 volt, so delta VD will be much smaller amount. So what is delta I by delta V? What is delta V by delta I? Is RD, right? The resistance of the diode. So delta I by delta V is 1 divided by RD. So you can see the slope changes from here to here. So 1 divided by RD is quite small here. That means RD is quite high. And here 1 divided by RD is quite large. That means the resistance is quite low. Okay, so you can change the resistance of this diode. So 1 by RD is DI divided by dV. What is I? We have the diode equation, or V divided by Vt minus 1. So by the way, Vt is the thermal voltage, okay? Usually it is 25 millivolt, or I should say approximately equal to 25 millivolt. Does anyone know how to differentiate it? How do you differentiate it? So I naught is a constant, so that goes out. The differential of an exponent is the exponent itself, but we have 1 by Vt there. So 1 by Vt e power V divided by Vt. Yes.
So there is a lecture of our project.
Oh.
Today we have to attend that, and in the next lecture we will change it.
What does it mean?
Actually, there is a clashing in between this lecture and the project lecture.
Which is that one?
Engineering project.
Okay.
We have that plan only for this week, but we will change for the next week. So there will be no clash for the next week. Only for this week we need to go there.
Okay.
It's engineering 600.
Okay. So do you want to go now?
Yes.
Okay.
Thank you, sir.
No problem. Huh? Yeah, it's, I mean, got used to everything. So. So, you can add and subtract 1 without any problem there, so which is 0. So that will give you, so what we want to make is this one. Very, what we have a familiarity there, 1 divided by Vt. Why keep writing Q there? Plus I naught. I naught divided by Vt, sorry. So this term is ID, right? So we can form 1 divided by 1 divided by Rd is equal to 1 divided by Vt plus Id plus I naught. And because I naught is very small, we can approximate it as 1 divided by Rd is Id divided by Nvt. N is the ideality factor, which is usually equal to 1. So we can write Rd is equal to Vt divided by Id. So this is a linear approximation for the diode, and we found the resistance at a very small section in that region. Okay, so if you find another small section here, you will get another Rd because your Id is different. Okay, so can you think of an application for this? So if you are given a diode and you are given this equation, 1 divided by Rd, or Rd is equal to Vt divided by Id, what device can you make out, or what product can you make out of it? You can make a variable resistor by temperature sensor, a thermometer. Yeah, so you can make a thermometer. So when you put it in a hot liquid, for it say, your Vt is different because it's not 25 MeV now. You have 50 MeV if it is 50 degrees, and keep your Id constant, and now you have a different resistance. Or your resistance changes, you measure the current flowing through it. So you have a thermometer, a makeshift thermometer.
Self-calibrating heater?
Yeah. So many applications like that. Okay, just in case in the future, zombie apocalypse, if you want a thermometer, there you go. Yeah. Okay, that was a single junction. If that wasn't enough, we have BJTs coming, which have 2 p-n junctions. Okay, have anyone studied thyristors or gun diodes? Yeah. So there you have 5, 6, 7 p-n junctions, right? So we go only up to 2 p-n junctions, BJTs. So before that, do you have any questions on diodes? Any questions? All right, if you still have questions, ask me after the lecture then. So bipolar junction transistors are 3-terminal devices, 3-terminal semiconductor devices. It's either a back-to-back or front-to-front p-n junction. So you can see here, this is a back-to-back p-n junction, 2 diodes connected, their anodes connected together, or 2 diodes with cathodes connected together. So this one is called the NPN BJT, and this is the PNP BJTs. So if you know NPN, same equations, same working principles, all are transferable to PNP BJTs. Okay. So in the last unit, there was a question which was PNP transistor, and somebody wrote me, "You are cruel," because in the example we done NPN, and I asked PNP for the final exam. But if you can do problems with NPN, you should be able to do problems with PNP. It's the same. So we will do both. So you saw in diodes, it requires quite a lot of steps to fabricate a diode, and you can imagine there are furthermore steps. So you start with the diode here, and then do the additional steps to create a BJT. So inside a BJT, you have a P-type. If it is a NPN BJT, you have a P-type base region sandwiched between two N-type regions. So one we call emitter, which emits carriers, and the other one we call collector, which collects the carriers. So you can imagine where would be the current flow, or not the current flow, where the carriers flow. So carriers are emitted by the emitter, and they get collected by the collector. Right? Easy to remember. So BJT has 3 working modes. It's a cutoff, saturation, and forward active. So let's So here is a BJT. We have the emitter here. Emitter has the arrow, and collector and a base. So I told you this NPN BJT is like 2 diodes back to back, right? I should draw it in a different color so you don't confuse. So there is no extra diode there. The base collector junction itself is a diode, and base emitter junction itself is another diode. So base emitter junction reverse biased and base collector junction reverse biased will give you a cutoff mode. Okay, so both diodes are reverse biased. So you apply a negative there, and you apply negative there. So what is the current? If it is if a diode is reverse biased, what is the current through the diode? It's 0. So there is nothing flows. So it's like an off mode or cutoff mode for the BJT. Okay, no current. And the saturation mode is just the opposite. You have base collector junction forward biased and base emitter junction forward biased. Now a large amount of current flows through both the diodes. Okay? And that is called saturation mode. So there is one more mode there are 3 modes. So one is cutoff, the second saturation, and there is another mode which is called forward active. Forward active mode. In forward active mode, base emitter diode is forward biased and base collector diode is reverse biased. So, you know, current will flow through this diode. Will current flow through that diode? Yes, is the answer. So that is unique about BJTs. Let's see why would current flow through the base collector junction, even though it is reverse biased. Okay? Let's look at the charge distribution for that. Maybe this one. So I told you emitter base junction is forward bias. That means you apply negative here and positive to the base, right? So as we explained before, now we are pushing the electrons and holes into the junction. So electrons are going this way and holes are going this way because it is forward biased. So of all the electrons that reach the base, some of the electrons will reach here and will fall through this reverse bias. Okay? Maybe I should draw it again. So let's just look at the conduction band. So you apply negative here to the emitter, just like here, negative to the emitter, and positive to the base, which is here. Now you are pushing electrons all the way up the hill here. Okay? And now the electrons are at the base. If the base width is tiny, it's a very narrow base, what will happen? The electrons will roll over and go down this potential and reach the collector. Right? Do you find it difficult? I mean, is it all right? Yeah. Okay. Just let me know. I can repeat it. Yeah. So the base to collector junction, the electrons, we call electrons drift through the base collector junction. Yeah, so that is why we have a current flow through the diode even though it is reverse biased. And that current is not flowing in the forward bias direction, it is flowing in the reverse bias direction. Okay? So again, looking at the charge distribution, I said we are pushing the electrons into here, and electrons are accumulating near this barrier, and some electrons will cross over to the barrier, and a lot of electrons here are next to this emitter, and then less number of electrons here, because whichever electrons happen to come here, they just quickly get swept away to the other side and to the collector. Okay, so that mode is the forward active mode, and that is important mode of the three for our application, because forward active mode is what we use for amplification of the signals. So when we use the BJTs as amplifiers, we use the forward active mode. Can you find any use for the cutoff and saturation mode? Switching and digital logic, TTL logic, we use the saturation and cutoff modes. In TTL logic, they don't like the active mode because active mode is where the most power dissipation happens. So in the cutoff mode, as you correctly said, the current is 0 and the voltage is maximum. So the power is voltage times current is 0. And in the saturation, voltage is close to 0 and current is maximum. But when you look at a power, which is the product of voltage and current, again it's very low. But in the forward active mode, there is a finite voltage and there is a finite current. So when the product is a large number. So in TTL logic, they want to reduce the power consumption. So if you stay in on or off mode, or saturation or cutoff mode, very low power consumption. But when you switch, you have to go through this forward active mode. That switching takes more power. That is why high power computers get heat up, because their clock frequency is quite high, the switching is quite high from on and off. So each switching creates power dissipation. Okay? Any questions so far? I know it's been a lot of things that we learned all compressed into a few number of slides. I'm expecting questions. You have questions? Any? Maybe later. Okay. I feel thirsty, but I don't know who kept it and when. All right. So here, let's say we increase the collector to base reverse voltage. So what does that mean? That means increase the voltage means you're bringing it down further, right? So instead of here, now you have something here. How does it change the collector current? Does it change the current really? Because the collector current is only the number of electrons that reached the flowing here, right? Just by changing the slope does not increase the number of electrons coming there. So that is the reason why changing that is the reason why the collector current is not dependent on the collector to base junction voltage. It only depends on base to emitter junction voltage. Okay, so it depends on only the number of electrons that's been injected into the base. So just like a diode, we have this equation which forms the basis of all other equations for BJT. It's IC equal to IS e power VBE divided by VT. VT is again the thermal voltage. And IS is the saturation current that again depends on the area and the width of the junction. So what happens so this is the width of the base. Okay? So what happens to the collector current if the width of the base was quite large? So if the width W was large, IS would be small. So if IS would be small, IC would be small as well. So that is the mathematical way of looking at it, but the physical way of looking at it is when you have all the electrons pushed on to the base, and the base is really long, the electrons don't reach into the other big valley, right? So it will just recombine there itself, get lost. But if the base was really narrow, all the electrons pushed up will immediately flow down to the deep reverse bias into the collector. Okay? So the IV characteristics of the BJT. So the collector current and also the base current, IB, because it is a diode, forward biased diode, it follows the same characteristics as a forward biased diode, a PN junction. And what happens on the other side, which is the output side, which is the collector to emitter voltage. So for small collector to emitter voltage, the collector current is small. So that means you have your EC emitter here and base here and collector here. For very small collector voltages, say here, there is no much of a valley there to say. So that is the small IC here. So only a very few number of electrons will go that way. But if you increase it, immediately start going up. So increase further, it does not affect that much. So the slope now, after reaching some certain point, the depth of the slope is not a big factor affecting the current. So it saturates. So that is why your IC saturates at some point. Okay? So let's look. So that was about the collector current, which is the main thing in BJT. Let's look at the base current. So what forms the base current? So there are two components for the base current. So one is, I told you, emitter is pushing electrons into the base. So that is one component. And another component is the electrons that reach the base recombine. And now we have a lack of carriers, or lack of electrons there, and you need to replenish electrons from the external circuit. So the two components there. So it's the same case as holes. So in an NPN transistor, this is the emitter, this is the collector, and this is the base. Electrons are pushed to the base, and at the same time, holes are pushed from base to emitter, right? So it's a two carrier transport. So these holes that come to the emitter, that constitute one part of the base current, this one, IB1. And those electrons that's coming from the emitter gets recombined with some holes that is already present in the base. And that has to be replenished from outside. And that forms the current IB2, which is the recombination base current. So the base current is a sum of these two. And the equation for base current is this IB is IS times this term times e power VB divided by VT, which is same form as IC. So you can say that IC is equal to beta IB. Beta being this additional term that you will see here. Beta is called the common emitter current gain, or HFE. If you look in the data sheets of transistors, you will see the term HFE. So does anyone remember the beta of BS 107? Yeah, it was around 250 typical value. So it can vary anywhere between 50 to 2000. So now let's look at the emitter current. So just using Kirchhoff's law, so we have collector current flowing this way and base current flowing this way. Kirchhoff's law says current is neither, basically say carriers are neither created nor destroyed, or current is the same. So you can say the IE is equal to IC plus IB. So for each node, the current entering the node is same as the sum of the currents leaving the node. So if we consider this whole BJT as a node, IC and IB are entering, so IE should be the sum of IC plus IB. So you can rearrange IB as IC divided by beta, just like what we saw in the previous slide. So you get this new equation with alpha. So alpha and beta are two terms that you will see, or two parameters that you see in datasheet, and these are used for designing circuits. And you can interchange. If you know alpha, you can find beta and otherwise. Yeah. So if you want to design a ideal BJT, what things you need to make sure? What are the few things you would do if you want to design a close to ideal BJT? First of all, what is a close to ideal BJT? No power loss. Alpha close to 1, alpha close to unity, and beta will be very, very high. Yeah. So how would you make beta very high and alpha close to unity? So that all depends on the design considerations, right? So we saw.
If you make the base region infinitely small, and
Yeah.
you make the collector region and emitter region.
Yeah, so here is the beta equation for beta there. So you make the base width very thin. That makes beta, because it is a reciprocal, 1 divided by that. So beta will be high.
And you just have nothing but pure electrons and pure holes instead of actual doped material.
Yeah, so you reduce Na, which is the base region doping, and increase Nd, which is the emitter region doping. So highly dope the emitter, very lightly dope the base, and make the base very thin, and then you have a close to ideal transistor. Okay? Now, we will look at the equivalent circuit in the forward active mode. So I said we have base to emitter, it's a forward biased diode. So there is a forward biased diode. So what's the property of a forward biased diode? The voltage remains more or less the same, right? So if you look at the IV curve, so this is voltage and this is the current, this is the IV curve. It is slightly like this, but the voltage remains more or less the same, even the current is 10 milliamps or 100 milliamps. When you look at the voltage, there is no much difference, very tiny difference. So we can say the voltage is more or less the same, and it comes around 0.7 volts. Okay, so it's a forward bias diode there. So we will make use of that fact, that 0.7, in when we design circuits. We assume there is a constant drop there. And on the collector to emitter side, we consider it as a constant, a dependent current source, not a constant current source, a dependent current source. And what is it dependent on? The the IB that is going in, because IC, that current is beta times IB. So here is a summary of all the three operating modes. So in the cutoff mode, there is no diodes, all reverse biased, nothing here and nothing here, no current. Okay, so this is for PNP, sorry, NPN, and this is for PNP. And in the saturation, both diodes are forward biased, and according to what we just discovered, it's 0.7 volt constant. So we can either write like a diode there, or you can just put a constant voltage, a DC voltage, which is 0.7 there. Okay, getting some response there. And same case here as well, collector to base. There is a constant voltage source there because both diodes are forward biased. And in the active mode, the base to emitter diode is forward biased, so you have a constant voltage source there, or a diode. In the base to emitter, you have a dependent current source, and the current source is dependent on the base current IB. And the same with the PNP transistors, but just the direction of the current is different. So these are some of the responses from you. Lightly doped emitter, it's hard to understand. Okay, let's move on to MOSFETs. So I want to take a 2-minute break, which you can make use by asking questions. 2 minutes, don't go anywhere, just relax. There's only half an hour left, so that's why 2 minutes.
Is the concept that you use for example, in a practical, say you have an Arduino powering MOSFET, you have the Arduino power voltage gate MOSFET, which then gates the power MOSFET. Is that something that you can how do you control power MOSFET?
So there are two ways, one using the intermediate or another directly powering. It's the low power MOSFET.
Like do you use a low power MOSFET control?
Yes, you can use
And
that.
then use that to control the high power.
Yeah. Yeah.
Okay, one question. You say there is something like two diode. Yes, and structure over C and E is very similar. Because we can use this use as C.
Okay, good question. I will answer it for the whole class. Okay. Okay, that was a good question. So the structure is, so this is still within that 2 minutes, okay? So the structure, collector and emitter, they look the same. They are PN junctions. And also here, emitter, base, collector, they are same. Can we swap it? So can we use this as emitter and use this as collector? Base being the same. Is it possible? Because? Yes. And what happens if we use the collector as emitter? Our beta will be very low. So the answer is emitter region is doped really heavily. Okay, so let's call it N++. And base region is heavily doped and, no, lightly doped and very narrow. So we call it P. And collector region is N-type doped, but not as heavily as emitter. So this is just N. So one is N++, and you have a P, and you have a N collector. So what happens when you swap it? It's just like what you saw in the expression for beta. Now, your emitter, which was previously a collector, is now here. The ND is small, right? So that makes this term large, which is under 1 divided by a large term, which gives you a small beta. Okay, so it won't be an ideal transistor. So you can try this in the lab. So take a transistor and swap the emitter and collector, and you will end up with a very bad transistor. It won't go, the transistor still work, but the beta will be very low. Okay? But that was a good question. Are you ready to learn about MOSFETs? Right, MOSFETs are another transistor. MOSFET stands for metal oxide semiconductor field effect transistor. So we have the structure of a MOSFET is like this. I can draw here. It's a semiconductor, usually silicon. And then you will have two N-type regions doped into that. So this is a P-type silicon substrate. You have two N-type regions doped onto that. Then you will have a oxide there, and a metal is deposited on top of it, which we call the gate, and this one as source, and this one as drain. So that is where the name MOSFET comes from. This is the metal oxide semiconductor, MOS, field effect transistor. So just like in a diode, in a BJT, emitter emits carriers. Just like that in MOSFET, the source sources the carriers, and the drain drains the carriers, and the gate acts like a gate. Okay, so when you apply, okay, this is a better picture there. When there is no voltage applied to the MOSFET, we have two N+ regions, source and drain, and in the middle we have the semiconductor. There is no channel. Does any current flow here? No current can flow there because there is no channel. And you know there are two PN junctions, one here and one here. Okay, this is a P-type, this is N, so the PN junction will be around here. So what happens when you apply a small amount of voltage at the gate? So this is the N-channel MOSFET, so you apply a small amount of positive voltage there. When you apply positive voltage, it will repel the holes, and the holes will go down. And that will create a channel for electrons there. So a channel can physically form between these two N-type doped regions. Okay, and now if you apply a voltage between the source and drain, there is a conduction path for the electrons from source can go through here and reach the drain, right? And the moment you remove that voltage Vg, the channel disappears, and now current cannot flow anymore. So once the channel is formed, so once you apply Vg, a channel is formed, and suppose you increase the drain to source voltage, VDS, between the source and drain, you apply a voltage that will form a current path like this. You keep increasing the voltage VDS, what happens? Your current also will go up. Right? So it's just like a conductor. from here to here, and now you increase this voltage, your current will go up, and it goes close to linear. So we call it a small linear mode, and it depends on VGS. So if you have a large VGS, that means you have a very thick channel. That means your resistance of the channel is very little. Okay, so your IV curve also will show that you will have a very steep IV curve. Okay. So what happens if you keep increasing the voltage VDS? So I told you we have a PN junction here and here, but because of the high gate voltage, we formed a channel there. But if we increase the drain voltage or to highly positive, what are we doing to the PN junction? We are reverse biasing it, right? So the depletion region here will keep expanding, or the reverse bias keep expanding. That competes with the charge accumulated here. So the width of the channel towards the drain will start to narrow down. Okay? So because of that, the curve will start to saturate like this. So it cannot keep going up and up, because the channel gets narrower and narrower, the resistance keep going up. So it goes like this, and at some point called the pinch-off voltage, the channel gets to a single point. At that point, it cannot no longer increase the current. The current remains the same, or the resistance. What is the resistance here? So no matter how much you increase the voltage, the current has no effect. So what is the resistance? No.
Doesn't it scale with VD?
It should scale not with VD. Close to infinity or infinity, right? So you double the voltage, but current is the same. Or say, let's say delta V by...
It's not really infinity, it's got two components, one of which is infinite. and one which is not.
Yeah. So let's say R is delta V divided by delta I. You double the voltage, so you have a finite voltage, but your delta I is 0. So you're dividing a finite number by 0, and you get infinite resistance. Or another way of looking at this is the slope. The resistance is 1 divided by the slope, because the slope is y divided by x, and y is delta I, x is delta v. So slope is delta I divided by delta v, which is 1 divided by r. Okay, so here the slope is 0. So 0 is equal to 1 divided by r, and r is equal to 1 divided by 0, which is again infinity. Right? So a MOSFET has 3 operating modes. So one is the cutoff mode, which is if the VGS is below some threshold voltage, the channel is not formed. So it need to reach to certain threshold voltage, usually somewhere between 0.5 volt to 1 volt. If you keep increasing up to 0.5 volt, no channel is formed, and beyond 0.5 volt, a channel is formed readily. That 0.5 volt is called the threshold voltage. Okay, so beyond the threshold voltage, a channel is formed, and now the current can conduct. So anything below the threshold voltage or VGS below VT, which is the threshold voltage, is the cutoff. So cutoff mode. And then if the VGS is above the cutoff mode and the channel is formed, depending on whether your channel is pinched off or not, you get the triode mode. Okay, triode mode has a varying resistance. So at low VDS, you have a very low resistance or high slope. And once the channel gets narrower and narrower, your slope is smaller and your resistance is higher. And at some point, at VD sat, where VGS minus VT is same as VDS, in that condition, the channel pinches off. And that pinches off means your channel, here you have a finite channel. Once it reaches here, the channel is just a single point. Now your resistance is infinite and your current can no longer increase. And that region is called saturation region. And in a MOSFET, it is the saturation region that we use for amplification. It is different from BJT's saturation region. In the BJT, we use forward active mode for amplification, but in MOSFET, we will use saturation for amplification. Okay? So don't confuse that. So what we looked so far is a enhancement type MOSFET. We will see what it is. So there are other types of MOSFETs. So that is, one is a depletion type MOSFET. So depletion type MOSFET is even when you don't apply any voltage, the channel is already there. The channel is formed by doping. Okay, so without any voltage, there is a channel. So if you just connect, without connecting the gate, if you just connect the drain and the source, there is a conduction path. And then you apply a voltage, and the channel will disappear. So you apply a voltage which dissipates the channel. So if it is an N channel, you will apply a negative voltage. So it repels the electrons away, and there is no channel anymore after that. Okay, so that is the depletion. So you deplete the channel. So that's the depletion type MOSFET. So what we have seen so far is enhancement type MOSFET. So there is no channel in the beginning. Now you apply a voltage to enhance the channel, or you form a channel, then enhance it. So that's the enhancement type. So symbols. So this is the symbol. If you look in the data sheet, you will see symbols like this for NPN and, N-channel and P-channel MOSFETs. But in this unit, we will follow the simplified symbol, which is also a standard symbol for MOSFETs. So N-channel MOSFET and a P-channel MOSFET. So question, what is the carriers, conduction carriers in N-channel MOSFET? Electrons or holes? Electrons. In N-channel MOSFET, it is electrons. So, and I told you the source sources the carriers and the drain drains the carriers. So here, the carriers are electrons. So the source sources the carriers. So that means source will send electrons in this way to the drain. And the direction of current is opposite to the direction of electrons. That is why the arrow here is the opposite direction. Okay, so the arrow always shows the direction of the current. And similarly, in the P-channel MOSFET, the carriers are holes, or the channel is made of holes. And the source sources those carriers, so the current flow this way into the drain. So that's why arrow is into. Okay, that's one way to remember that, which symbol to use for N-channel MOSFET. So the thing in the box is grayed out. So you don't really need it, but if you are curious how we got this equation that governs the current through a MOSFET. You can look at it. It's quite simple. It's just follows this equation. Current is charge time velocity. Okay, so charge is here, and the mobility, which is the electron velocity, is here. And you multiply them, and you get the equation, this one. Okay, so this is the equation for the equation for drain current in a MOSFET for small VDS. So there are a few things that you need to remember. One is a transconductance parameter, which is this term here. And there is also a process transconductance parameter, that is a transconductance parameter without the aspect ratio. So aspect ratio is the width of the gate divided by the length of the gate. Okay, if you don't, so this is the length of the gate, and this is the width of the gate. Has everything to do with the structure of the MOSFET. So what happens when you have a large VDS, so when we go to the saturation, what governs that diode current? So that equation, again, I told you the channel tapers to one end. So channel was like this before. Now the channel became narrow at one end and wide on the other. In that case, we cannot use a constant channel width, so we need to use the average. So that will give rise to this term, and that equation, the previous equation, gets modified like this. So that gives us three equations, or two equations, one for the triode mode and one for the saturation mode. And because we use the MOSFETs in saturation mode for amplification, this would be the most important equation that we need to work with. Okay. So how about the equivalent circuit for a MOSFET? So in the BJT, we had between base and emitter, we had a diode. In this case, there is nothing there. Why is that? Because of the oxide there. So we had a oxide between the metal and the semiconductor, and oxide is a dielectric and no current can flow through the oxide. So there is nothing there. So there is no gate current. So gate current is equal to 0. Okay. What can you infer about from that? What can you infer about the input impedance of a MOSFET? It will be very high, right? Because the current is 0. So whatever voltage you apply, the current flowing through it is 0. So it's an infinite gate resistance there. And similarly to the BJT, we have a dependent current source, which depends on the voltage at the input. Okay? And because it may not, so this was the ideal case, we will have a constant ID which saturates and does not increase at all. But in non-ideal cases, we will have still a finite resistance there. Okay, here the slope is 0 and resistance is infinity. And here is slope is finite, so resistance also will be finite. So in that case, we will have to include an additional resistor called early resistor. early, so that is because of the early voltage, which is the voltage. If you track down this curve to the voltage, that voltage is called early voltage, usually denoted by VA, and the resistance is corresponding to that voltage is the early resistance that you need to include, which is between source and drain. Okay. So we have 7 minutes. So you can ask questions. Before that, I want you to talk about the labs. So if you didn't listen or you were not here when I talked about it, so we need to do some pre-labs before you start the labs. So pre-labs will carry 20 marks out of the 6 day for the lab sessions. The iLearn already has now the pre-labs questions or work modules for the next lab, which is in next. Is the next Thursday? Next Tuesday? No, Tuesday is the first lab. The Tuesday, so you need to work on the pre-lab, then come to the lab, okay? And this year we are using software called LT Spice, which is a free software. So you can, and there are links to download the software on iLearn. You can go to that site and download LT Spice and start playing with that. Okay. Yeah, I'm here for next few minutes for taking questions. And I will see you all in the lab and also next class. I don't know. I never saw the name of the students. Hey. This lecture, okay. So you can always catch up in the call. It will be documented. It's recording here. So yeah, this is recorded. Maybe you can check it tomorrow whether this lecture was recorded, and then if not, just let me know. Most 99% it will be recorded.
And then was it going to have like the updated PowerPoints?
Yes. Yeah, so you will have a few videos that you need to watch and learn before the next lecture. Mini exam. That will be during the lecture. And that will be after 1 hour. So the first hour we will use for a survey, and the second half will be the exam. No, first week no lab. Lab from second week.